Hello, in this podcast we're going to take an in-depth look at work and the work-energy theorem. First, we're going to look at the definitions of work and energy and some other key terms associated with them. Then we'll take a look at vector multiplication, specifically work and the dot product. Moving on from there, we'll learn how to calculate work performed by constant forces and how to calculate work performed by forces that are not constant. Finally, winding up with the work-energy theorem and how we use it to analyze motion and energy. Let's get started. Work is the transfer of energy between particles by applying a force parallel to the particle's displacement. This portion here, parallel to the displacement, is important, and we'll talk about that more in a minute. Energy, it's a quantity that flows among storage mechanisms within a particle and between particles. It also causes change. No change occurs in the universe without a flow of energy. Storage mechanism, this is a means of storing energy in a particle. The major storage mechanisms are kinetic, thermal, gravitational potential, elastic potential, chemical potential, and dissipated. To flow the energy between storage mechanisms, we need to have transfer mechanisms, and this is a means of flowing energy between storage mechanisms within a particle and between particles. The transfer mechanisms are work, heat, and radiation. And finally, I want to talk about mechanical energy. We use this term a lot when we talk about energy flow in mechanics. The primary mechanisms involved in mechanical energy are work as the transfer mechanism. Mechanical energy is the amount of energy stored in the kinetic, gravitational potential, and elastic potential storage mechanisms of an object. When friction is involved in our analysis, heat and radiation will be transfer mechanisms involved, and dissipated is a storage mechanism where some of the energy flows. Let's move on and talk about work and the dot product. So work is equal to the force vector multiplied by the displacement vector. There's two types of vector multiplication. There's dot product, and that's important when the quantity we're trying to calculate is a function of parallel vector components, whereas the cross product is important when the function of the quantity we're trying to calculate is the perpendicular components of those two vectors. Work is the quantity created by force acting parallel to a displacement, so we're interested in the dot product when it comes to calculating work. If we have an example here, we have an object and it's moving along this displacement vector caused by this force vector. Notice they are not parallel to each other. We can't simply multiply the magnitudes of these two vectors. What we do to get the cross product is we take the magnitude of the force vector times the magnitude of the displacement vector times the cosine of theta. Theta is measured starting at the displacement vector and going counterclockwise to the force vector. If you have multiple forces, you're going to determine the net force vector. You're going to take that magnitude multiplied by the displacement magnitude multiplied by the cosine of theta, which is the angle between the displacement vector and the net force vector. Notice that if we take force times cosine theta, that gives us the portion of the force vector that is parallel to the displacement. Here's another case, and I'm just pointing this out that you can use negative theta if you measure clockwise from the displacement vector to the force vector. Work is a scalar quantity. Its SI units are Newton meter, also given a special term joule. Forces that are perpendicular to the displacement perform no work. And in our formula, of course, that's because the cosine of 90 or 270 is 0. Let's take a look here. We have the wagon being pulled by a boy. There's a normal force and a gravity force acting on the wagon. Those are perpendicular to this displacement vector, so those two forces perform no work on the wagon. Force and displacement in the same direction, the work is positive. Now you may be saying, wait a minute, I thought that work is a scalar quantity. And it is. When we say that work is positive, we mean that the energy is flowing from the particle that's exerting the force into the particle that's feeling the force. So in this case, we have the boy, his tension force pulling the wagon. There's an X component of that that is in the same direction as the displacement. So energy is flowing out of the boy into the wagon through the work mechanism. Now let's take a look at the friction force. Notice that the ground is exerting a friction force that is parallel to the displacement vector but in the exact opposite direction. In this case, work is negative, and that means that the energy flows into the particle exerting the force and out of the particle that's feeling the friction force. So in this case, the friction force is causing energy to flow out of the wagon and into the ground. And of course, it would be going into the ground and the atmosphere in the dissipated storage mechanism. Let's move on and look at work done by constant forces. When the force exerted on the particle is constant, it's relatively easy to calculate work using this formula. Here we have a box that is pulled 20 meters by a rope with a tension force of 100 newtons. The weight of the box is 300 newtons. The friction force is 40 newtons, and of course the normal force is 300 newtons. The question we're going to answer is how much work did each force perform on the box? Looking at the tension force, we use our formula, recognizing that the angle between the tension vector and the displacement vector is 60 degrees. We plug in our numbers and wind up with 1,000 Newton meters. Also, that would be 1,000 joules. Next, looking at the gravity force, we notice that the angle between the displacement vector and the gravity force is negative 90 degrees, or 270 degrees. That's going to yield no work, because this force has no component parallel to the displacement vector. For the normal force, it's going to be the same thing, since that is also perpendicular to the displacement vector. For the force of friction, we have an angle of 180 degrees. That's going to cause this to be a negative 800 Newton meters. Remember, the negative sign here means that the energy is flowing into the object exerting the force and out of the object receiving the force. So since the friction force is the ground acting on the box, in this case 800 Newton meters of energy is flowing out of the box and into the ground. Add up all these work totals, we find out that the net work performed on the box is 200 Newton meters. So it gained 200 Newton meters in mechanical energy. Looking at a different situation, here we have a box that is sliding down a frictionless ramp. The box has a weight of 300 newtons and its displacement is 10 meters, and we want to know how much work did gravity perform on the box. So we have our force vector, our displacement vector, we have our angle theta, which is going to be 60 degrees between the two vectors, and we can calculate the work as 1500 Newton meters. Let's move on to varying forces. If the force changes as the object is being displaced, we cannot use the formula from the previous slide. Instead, we have to use an integral because the force is a function of the displacement. These would be our two formulas. This one is if there's a single force acting on the object, or you want to calculate the work performed by a single force. This equation is used if we want to calculate the net work performed by multiple forces. Springs are a popular example in AP Physics to use when studying varying forces because the force exerted by the spring is proportional to the displacement of the spring from its normal or equilibrium position. The negative sign in front of the spring constant exists because the force the spring exerts on the object is going to be in the opposite direction of the object's displacement. Here's our generalized integral equation for work performed by a spring. You can see we wind up with negative 1/2 times the spring constant times the final position squared minus the initial position squared. If the spring is starting at its equilibrium or normal position, then this x sub I is 0. However, in some instances you're going to have to analyze problems where the initial position is not the spring's equilibrium position, and then this x sub I value will not be 0. Here we have a problem. A spring obeys Hooke's law and has a spring constant of 25 Newton meters. How much work does the spring perform as you stretch it 20 centimeters beyond its equilibrium length? So we go ahead and set up our formula. Notice our limits of integration are going to be x sub I and x sub f. So it started at its equilibrium length, so that's 0, and it was stretched 0.2 meters. After solving the integral, we find out that the spring performed negative 0.25 Newton meters of work. The negative sign meaning that energy flowed into the spring and it was stored in the elastic potential mechanism. Let's look at another problem. So now we have a block attached to this spring, and the spring is stretched 50 centimeters beyond its equilibrium length. How much work does the spring perform as it contracts to 25 centimeters? Here we have the spring stretched 50 centimeters beyond its equilibrium length. We let go of the block, and of course the spring accelerates the block back to the left. How much work was performed as the block moved from 50 centimeters to 25 centimeters? We set up our integral. Notice here the limits of integration are the starting position, which was 0.5 meters, and the final position, which is 0.25 meters. After solving the integral, we find out that the spring did 2.34 Newton meters of work on the box. The fact that there's a positive sign here means that the energy went into the box and it was stored in the kinetic mechanism. Let's move on and look at another way of calculating work done by variable forces. We can use graphical methods to solve variable force problems because the integral used to calculate the amount of work done is equal to the area under this curve. For example, suppose we had experimental force displacement data. We plotted it and we wanted to find out how much work was done in moving the object from 5 meters to 15 meters. Here's our plot of experimental data ranging from 0 meters to 15 meters displacement. We're interested in the work done from 5 meters to 15 meters, so we need to calculate this shaded area. Using our different formulas, we find out that the total work done was 262.5 Newton meters. Here's an important tip. If you're struggling to solve an integral, you can graph it in your calculator and find the area under the curve. This is a completely acceptable way of solving problems when you're given numerical values. So you can remember this not just for work problems, but anytime you need to solve a difficult integral. The work-energy theorem is a very important theorem and tool to use in solving mechanics problems. It relates forces acting on a particle to the velocity of the particle. It's important to use when we have problems that the forces are so complex that Newton's second law is difficult to use to determine the motion of the object. The theorem is the net force is equal to the change in the object's kinetic energy. Let's take a look at how this theorem was derived. We know that net work is equal to the integral of the net force times the displacement, evaluated from the initial position to the final position. Newton's second law tells us that the net force is equal to the mass times the acceleration, and we know that acceleration is dv dt. So if we substitute this into the work equation, we wind up with the net work is equal to the integral of m dv dt dx. We can rearrange these differentials and get it in the form of mass times dx dt dv. Now when we change the differential from dx to dv, we need to change the limits of integration from x sub I to v sub I and from x sub f to v sub f. Notice this dx dt is the definition for velocity, so we can rewrite this integral as mass times velocity dv. And when we solve this integral from the initial velocity to the final velocity, we wind up with 1/2 mass times the quantity final velocity squared minus initial velocity squared. This is the expression representing the change in kinetic energy. Let's move on and look at some problems. First, we'll try a simple kinematic problem. A man's pushing a 50-kilogram box across the floor. The net force acting in the horizontal dimension is 80 newtons. The box is initially at rest. How fast is the box moving after 10 meters? We'll go ahead and set up our work energy theorem, and we'll rearrange this to solve for the final velocity. And then we'll plug in our numbers, and we wind up with a final velocity after 10 meters of 5.66 meters per second. Now, this problem would have been very simple to solve using Newton's second law and the kinematic equations. But let's move on and look at a more difficult problem that would be challenging using Newton's second law. In this scenario, we have a 1 kilogram block that's launched across a table by a spring that's compressed 0.2 of a meter from its equilibrium position. The spring constant is 20 newtons per meter. We're going to assume friction and the spring's mass are negligible. How fast is the block moving as it leaves the spring? So the block will be leaving the spring when the spring reaches its equilibrium position. We have to use our integral form to calculate work because the force the spring exerts on the block is not constant across the displacement. And we wind up with this equation, which we rearrange for the final velocity. And we plug in our displacements. Notice in this case the initial displacement was negative 0.2 meters because we're assuming that the spring was compressed to the left, which is the negative direction. And the final position was when the spring was at its equilibrium length of 0 meters. We wind up with a velocity for the box of 0.89 meters per second. Using Newton's second law and the kinematic equations, this would have been a more challenging problem to solve. However, it's a relatively easy spring problem. So make sure you understand this process because you'll see much tougher spring problems than this. Well, this ends our podcast on work. I hope it's helped you understand the concept, and have a good day.